Good morning, good afternoon, and good evening wherever you are. I'm the first author of this paper. Please call me Edison. I'm currently a research assistant professor in the Hong Kong British University HKBU. Here I will present this paper called Fast Augmentation Algorithms for Network Kernel Density Visualization. Before we talk about network kernel density visualization, let's review what is kernel density visualization, KDV. As you can see here, there are many black dots in this region. Each black dot represents the location of a crime event. Some representative examples can be robbery, commercial burglary, and motor vehicle theft. The goal of KDV is to predict the crime rate of a given location based on the kernel density functions, as shown here. As you can see that we can put the pixel, which can be the Leong values, into these equations, and it outputs the density value for this pixel. Based on this density value, we can color this pixel. Using this map as an example, we can find that the red color here denotes the high density region, which means these regions can be more risky. Now, let's talk about some representative applications of KDV. The first one is crime hotspot detection, which I've mentioned before. Here it shows the crime hotspot map in Atlanta, USA. The second one is the traffic accident hotspot detection. Here it shows the traffic accident hotspot map in New York City, USA. The third one is disease outbreak detection. Here it shows the distributions of COVID-19 cases in China. Although KDV has been extensively used in a wide range of applications, there are some weak points for using KDV. First, KDV ignores the row network. As you can see in the first figure, even though Q1 and Q2 are close with each other in terms of Euclidean distance, the short distance between Q1 and Q2 can be large. However, the kernel density function of KDV is based on the Euclidean distance. Therefore, this method can estimate the density values of Q1 and Q2 to be similar, which overestimates the density value of Q2. Why? As you can see here, there's no black dot near Q2 in this row network. Second, KDV cannot correctly identify which row segments are the hotspots. The method tends to color the large regions as the hotspot. You can observe that there's a large black region here. Let's look at the second figure. Even though the main row can have the high density of traffic accidents, the small rows which connect to the main row may not necessarily have the high density. However, KDV normally colors a large regions with high density. Therefore, it cannot correctly identify which row segments are the hotspot. That's why some geoscientists propose the network kernel density visualization, NKDV, to overcome the weakness of KDV, which I've mentioned before. First, they divide each row in the row network G equals to VE into a set of pixels. Then they color each pixel Q based on this modified kernel density function. As you can see in this equation, they replace the Euclidean distance with the shortest path distance. Using the previous toy examples for illustration, you can see that this is the new hotspot map. Based on this modified kernel density function, you can find that Q1 has a high density value and Q2 has a small density value, which are more reasonable. Therefore, this approach can overcome the weakness of KDV. However, there is one drawback for using NKDV. What is that? NKDV is slow. Therefore, many researchers complain about the inefficiency of this method. Here we quote two papers for that. In this paper, one, they mentioned that having efficient approaches to analyze spatial point patterns on linear networks is a welcome issue. Another paper, two, mentions that the methods for computing NKDV all tend to be very time-consuming, especially for large datasets. That's why we need to have this paper. Here we summarize the contributions of this paper. First, we developed the time complexity optimized algorithms for generating exact NKDV. Second, all our methods achieve at least 5 to 10x speedup compared with the state-of-the-art methods. Moreover, our methods do not incur high space overhead. Now, let's summarize two state-of-the-art solutions for generating NKDV. The first one is the range QV-based solutions, ArcGIS. The main idea of this method is that it avoids scanning data points that are out of range. That means distance G QPI is bigger than 1 over gamma. Using this figure as example, the blue dots are the data points that are within 1 over gamma. Therefore, only these blue data points can contribute to the kernel density function. ArcGIS avoids scanning these black dots and also the white nodes here. Even though ArcGIS can practically improve the efficiency of generating NKDV, this method still needs to scan all data points and cause the shortest path algorithm for each Lexo Q in the worst case, which takes OL times TSP plus N time, where L, TSP, and N denote the number of Lexos, the time for the single short-size path algorithm, for example, Dijkstra algorithm, and the number of data points in the row network, respectively. Now let's talk about the second one. The second one is the shortest path sharing solution, SPS. The idea of this method is that it shares the shortest path distance for those Lexos in the same edge. Using this figure as an example, those shortest path distance, that means in this dashed lines, can be shared to all Lexos in this edge AB. Although SPS is simple, SPS can achieve the smaller time complexity OE TSP plus NL compared with ArcGIS. Why? You know each edge contains more than one Lexos. Therefore, this L is bigger than this magnitude E. This explains why SPS is theoretically faster than ArcGIS. After we understand the general ideas of the state-of-the-art solutions, now let's talk about the general idea of our solutions, called Aggregate Distance Augmentation, ADA, which is super simple. The idea of our method is to augment these aggregate terms, that's meant here, for each data point in each edge of the row network. Based on these aggregate terms, for each point, our paper shows that we can efficiently compute the kernel density function value for each Lexo. Then we further show that this ADA method takes O magnitude E times TSP plus L log N over E time to generate NKDV. Here we omit the details for the derivation and the analysis. If you are interested in this work, you can read our paper. Now you may ask, okay, we have this time complexities for ADA. Then so what? Why do we need to care about that? The main reason is that it shows that our method ADA is theoretically better than the state-of-the-art solution. Now let's check it. You can see that the first terms in these two expressions are the same. Now let's check the second term. Is this one smaller than this one? Okay, you need to know that O log N over magnitude E is more than O N over E. Now, let's multiply magnitude E times L in both sides. Then you can conclude that O magnitude E L log N over E is more than O N L. That means the second term here is more than the second term here. Hence, we show that ADA is better than the state-of-the-art solution. In our experimental studies, we have utilized 4 large-scale view datasets for testing. Here, since our method ADA is theoretically faster than the state-of-the-art solutions, ADA can significantly improve the efficiency for generating NKDV compared with the state-of-the-art solutions, ArcGIS, and SPS. To conclude, we developed efficient algorithms that can reduce the worst-case time complexity for generating NKDV, and our methods achieve at least 5 to 10x speedup compared with the state-of-the-art solutions. These are 4 future directions that we plan to work on. If you have any questions, please ask us.